made up of two things, matter and energy. Is energy is exciting? Absolutely. Because there are so many different forms of energy all around us. Today, our daily life are highly dependent on electrical energy. If you look around you, you can see lights, fans, TVs, refrigerator and computer, even mobile phone. Everything is running on electricity. So this is one type of energy which we see in our everyday life and which is the most dominant one among the other types of energies. Campfire is going to use the firewood and a matchstick. Both of them are having the chemical energy stored inside them, which in terms of reaction giving out the heat energy to us to make us feel warm. So here the chemical potential energy, the heat energy, the light what we are getting, all of them are a kind of energy what we have. What is the difference between a glass of cold water and a glass of hot water? Ouch! The glass of hot water has more heat energy than the glass of cold water. Similarly, when you burn something like coal, petrol or diesel, it is also giving you the heat energy. None of us cannot be able to forget about these two names. The nuclear bomb is dropped by an American soldier which killed 80,000 people, which released a very huge amount of heat and light due to the nuclear explosion. Once again, that nuclear explosion is a kind of energy which is the nuclear energy. So about all this type of energies and the principle and conservation of this energies only we are going to explore in today's session. Six 6.9 The potential energy of the spring. So in this case we are going to consider a spring which is attached with a mass of m, and compared to the mass of the m, the mass of the spring is going to be less. So the first assumption in this case is the spring is going to be taken as massless, and this spring is having two edges. One of that has been attached with the wall and the other one has been attached with the mass. So the first one what we are seeing here is the first case where the spring is at its rest state. That is, the spring is not going to move. This is how it's fixed. That is, this is going to be the initial position of the spring. When the spring is at initial position, the net force acting on that is going to be 0. That means that there won't be any restoring force also will be acting on the string. So f of s is equal to 0, as well as the spring is at the initial position, x is equal to 0. That is, the spring is being placed on the horizontal surface which is taken as the x-axis. So exactly on the origin the mass is being placed now. When we are going to take the second case over here, we are supplying a force to expand the spring. That is, we are pulling this mass away from the equilibrium position, that is x is equal to 0. As a result of it, the spring is getting elongated. This elongation is due to the force what we supplied over here. As a result of it, it's just moving with the small velocity v. When the object is going to receive a force and it's going to obtain a velocity v, once you're going to leave this mass now, then the spring will try to get back to its original state, which will be x is equal to 0, that is the initial position of that. The force which is pulling this mass back towards the initial position is called as the restoring force of the spring. The restoring force is the force which pulls back the object to its original state or initial state. So here for the spring, the restoring force is going to be given by the formula F is equal to minus kx. Here the spring is going to be obtain the displacement of xm from the 0 position, so that the x is being replaced by xm over here. And we know that work done will be given by force into displacement. So with the help of that only we are getting this work done, which will be working out now. Then in the third case, so we are having three cases. Case 1, the spring is at rest. In case 2, the spring is elongated by an external force. In case 3 also there is an external force is going to act, but it will make the object to have a quasi state, which means that we are supplying a force to compress the spring, which will make a very slow movement in the object. In this case also the spring is going to displaced, but not along the positive x-axis, it's along the negative x-axis. That compression length is also of xm. So once again the force is going to be given by what formula? F is equal to minus kx only, but it is in the negative direction, so the x will be replaced by minus xm, which gives us the answer as Fs is equal to kxm. Once again for that only we have got this displacement by using the formula F is equal to work done is equal to force into displacement. So let us discuss how we got the work done for each case. So when I'm going to take the case 1, in the case 1, what is the force I'm going to have? Restoring force I'm going to have is 0. So if I'm trying to find out the work done in the first case, then my work done will be given by force into displacement, that is change in that position. So obviously 0 into 0, which is going to give me the 0 joules of work done. When I'm coming for the second case over here, the case 2 is going to hold the force of what? F is equal to minus k into xm, where in the case of the elongation we are doing this. Suppose if you are trying to find out the work done for the overall displacement what has been done, that is during that oscillation, then the work done will be given by the formula integral of initial position to final position. What is the initial position here? 0. What is the final position? xm. So 0 to xm times what we'll be writing here? The restoring force into displacement, where we know that the restoring force is going to be given by the formula minus kx into dx. K is a constant, so let us take the constant out of this. If I'm taking the constant and minus sign out of it, then I'll be having integral of 0 to xm x dx. So I have to integrate x with respect to dx, where whenever I wanted to do the x with respect to dx, then I can use the formula x power n is equal to integral of x power n is equal to x power n plus 1 divided by n plus 1. So if I'm going to use this formula over here, my work done is going to be of minus k into, instead of the x what I have over here, x only, n now what I have, 1. So 1 plus 1 divided by 1 plus 1, the whole limit tends to 0 to xm. That means that x squared by 2. So I'm just taking the 2 out, which is k by 2 now, and x square should be getting the limits, the lower limit and the upper limit. Lower limit is 0, so we will not have any change in the value of it, which gives us the value of minus k xm square divided by 2. So what is the work done we have over here is nothing but minus k xm square by 2. That's what the same work done what we have over here. So we have proved it for the case 2. The same thing only we are going to do in the case 3 as well. So when we are considering the case 3, the same thing only we are going to have, which is nothing but the restoring force will remain same, but it is going to be a compression which is along the negative x-axis. So our x displacement, that is the compression length, will be given by minus xm as it is in the negative x-axis. That is, it's compressing. So the x should be taken as minus xm. Therefore the restoring force Fs will be given by minus k into minus xm, which is going to give us the value of that as kxm, which will become plus. Now I wanted to find the work done again. So the work done will be given by, once again, the same formula, integral of what is the lower limit, what is the upper limit we are going to have, 0 to what I'll be having over here, xm only, and it will be given by force into displacement. Here the force is going to be kxm minus, kxm into displacement, which is dx. Then the k is constant. When we are taking it out, we are going to have the integral of 0 to xm dx. So which is going to give us the xm square. By substituting the limit also we will get the same thing, which means that the answer will be kxm square divided by 2 to us. So that's what the same work done what we have for the case 3. Instead of considering the spring and the force over here, if you are going to have a graph for this spring case, all these 3 cases, if you are going to have a graph, then we know that restoring force is going to be directly proportional to the extension. That is what is the Hooke's law is telling us. So the restoring force is going to be given by minus kx. That means that the elongation or the compression, the extension length, is directly proportional to the restoring force, is the Hooke's law. So when we are considering the case of the spring over here, according to the compression, elongation and the initial position of that, we could able to see that when the object is going to get elongate, the value of that will be in the positive quadrant of the force and the distance graph. The force is being taken as in the y-axis and displacement in the x-axis, and when it's going to be come for the origin, it will be over here, and then the compression will be in the negative quadrant over here. When we are trying to find out the work done by the spring with the help of the graph, then the graph must be like this, as I have shown you in the previous figure, that it is going to be having a elongation, and it is going to have the initial state of it, and it will be going for the final state of it. So along the y-axis, what I'm taking over here is nothing but the restoring force, which is going to be minus kx. Along the x-axis, we are going to have the displacement of the object. So when I'm trying to find out the displacement of the object over here, it's going to be a force distance graph. From a force distance graph, if I wanted to find the work done formula is force into displacement. So if this two should be multiplied with each other, then I have to find the area under the graph. So when I'm trying to find out the area under the graph, the area over here is going to be a triangle, so that it will be given by the area of triangle. When I'm writing the area of the triangle over here, formula for that is half times b times h. Here the base is going to be of the elongation length or the compression length what we had. So 0 to xm. Over here also 0 to xm it will be. So the base is going to be given by xm, and the height is going to be given by the force. What is the force value we have? So that is going to be of minus k xm. Up to the xm limit only we will have that force, right? So the work done is going to be given by minus k xm square by 2 according to the graph also. So here we should understand a fact that the force, that is the spring force what we have over here, the restoring force what we have over here, depends upon what is the initial state. X is equal to 0, and it's going to go to a final state of xm. So the conservative force is nothing but the one which depends upon the starting and the ending point, not on the path. So either compression or elongation doesn't matter, it's going to give you the same work done. That means that what is the restoring force we have over here is the conservative force. For example, if you are going to take that, initially the same spring case let us take. So we are having the spring, and the spring is being attached with the same mass over here. Initially it is going to be at the position of xi. After extension or compression, the spring is going to reach the position of xf. So from the position xi to xf, if it is going to move, then the work done, if I'm trying to find out, work done will be given by initial position to final position integral of f of x into dx, where our f of x once again will be given by what formula? Minus kx only over here, in terms of the elongation or compression. So if I'm going to take that as xi to xf minus kx, minus can be out, so minus kx into dx I'm going to have. So what is the resultant of that? I'll be having here is nothing but minus k will be in the outside. By integrating x, what we'll be getting is nothing but x square. So x square by 2, the limits will be xi to xf. That means that I will be having minus k x f square by 2 plus k into x I square by 2, or it can be written as work done is equal to k xi square divided by 2 minus k xf square divided by 2. So it is proved the work done will be given by the force into displacement, or other way you can say that as the change in energy will be giving you the work done according to the work energy theorem. According to the previous definition, we got that the work done is equal to kx square by 2, or it can be taken as the potential energy of the spring as well. So if you are taking the potential energy of the spring as kx square, then the rate of change of potential energy will be negative, as it's a conservative force. That's why I have written as the minus sign over here. So minus dv by dx must be equal to, what is the one we have here? D by dx of, there will be a minus sign, and I will be having kx square by 2 over here. So if I'm taking the k out, minus k into, and 2 also constant, so we can take it out. So minus dx squared by dx. Then whenever we are going to have the x power n differentiation, then the formula for that is x into x power n minus 1. So I'll be getting the answer for the above one as minus k by 2 into 2 into x power 2 minus 1. So this 2 and this 2 will get cancelled. So what is the rate of change of potential I'm going to have is nothing but minus kx, or we can write that as dv by dx is equal to kx, right? So the rate of change of potential energy will be given by the restoring force associated with the object. Now if you are going to consider the same case, the object is going to move from xm to minus xm, or minus xm to xm, then what is the net energy we are going to have here? So when we are talking about the net energy, the total potential energy associated with that for any displacement kxm square by 2 must be equal to the potential energy plus kinetic energy of the spring. According to conservation of energy, the total energy will be given by the kinetic energy plus potential energy of the object. Here the kinetic energy is going to be taken as half mv square only. The potential energy of the spring, we found that as half kx square. So over here we have the half on all the sides, which will get cancelled, and when we are trying to write the rest of it over here, it will be given by kxm square is equal to mv square plus kx square. So in this case, if you are going to take that the object is going to be at equilibrium, that is, it is at the initial state. What is the value of the x? It will be 0 at equilibrium. At equilibrium, the value of the x is going to be 0. So we will be having the equation as kxm square is equal to m. If it is going to be the velocity about that mean position, it will be vm square. So if I'm trying to find out the vm square will be given by kxm square divided by m, or v is equal to root of k xm divided by m. Note that the k by m has the dimension of t power minus 2, and our equation is dimensionally correct. The kinetic energy gets converted into potential energy and vice versa. However, the total mechanical energy remains constant. So let us look into this total energy conserved with the help of another graph. So when we are trying to plot the graph for the same thing, for the compression and the elongation together, when the spring is going to be vibrating, that is when it's going to be elongated or compressed, it will be trying to restore its position. So during that restoring, when the object is going to come for the mean position, it will try to have a motion associated with that due to the elongation or the compression. So whenever the object is going to be at the initial state, it will be having the higher kinetic energy, and because it is in motion, it will be having a zero potential energy. Here the blue one represents the potential, the red one represents the kinetic energy. Same way, either the maximum compression or the elongation the object is going to go. If it is going to be the compression or elongation, in both the cases, at the extreme position, the object will be at rest. That means that the potential energy of that will be high and kinetic energy of that will be low. That's the same thing for the other extreme as well. So this graph totally shows you that what is the kinetic energy maximum you have at the time potential energy is minimum. Which means that if you are trying to find out the total energy of the object, that will always be constant. That is, it is the addition of kinetic energy plus potential energy. The parabola over here shows the potential energy and kinetic energy variation of the block and the Hooke's law associated with that. 6.10 Law of conservation of energy, where we can see few examples over here that the roller coaster 6.10 Law of conservation of energy. Here we can see few examples where the energy is being utilized. For example, in the roller coaster ride, we are going to have the object at different height. So when it's going to be at its maximum height, it will have higher potential energy, and when it's going to move towards the down, it will have high kinetic energy. So initially, whatever stored in the form of the potential energy, that is going to be converted into kinetic energy when it's going to change its position. Similar way, when we are coming for it over here, in the dam, the water is stored as the potential energy. When it started moving, that's converted into kinetic energy. So this conversion is not only possible between potential and kinetic energy, it is also possible in other ways as well. Here we are having a battery which is having a chemical energy stored inside it. With the help of that chemical energy only, the electrical energy is being produced, and that's been converted into a light energy finally in the bulb. Same way, in this firewood, the wood is being made up of with hydrocarbons, which is a kind of chemical potential energy stored inside it, which is getting burned and releasing out the heat energy. So whatever the energy we have, that can be converted from one form to another form, but energy cannot be created on its own or can't be destroyed. One form of energy can be converted into other form of energy. So when we are talking about the principle of conservation of energy, over here the energy associated with any of the object will remain constant. So if you are going to take our universe as an isolated system, then the total energy of the universe is also constant. What is the energy lost by one part of the universe? That will be the energy gained by the other part of the universe. In general, if you wanted to say, there is no proof for this principle of conservation of energy. As well, we don't have any violation as well for this till now. So in general, the principle of conservation of energy or the law of conservation of energy is nothing but energy may be transferred from one form to another form, but the total energy of the isolated system remains constant. Energy neither be created nor be destroyed. There are so many different forms of energy is there. We will look into few of the types of energy over here. The first one, nuclear energy. The energy released in the process of forming a nucleus or disintegration of the nucleus is called as nuclear energy. Generally, the nuclear energy will be termed or will be found with the help of the Einstein's equation, which is the E is equal to mc squared. We used to call that as mass energy equivalence. So E is equal to mc square. So basically nuclear energy is the energy released during any of the nuclear reaction. It may be a nuclear fission or fusion. When we are talking about electrical energy, in the previous one we were talking about the atom and the protons and neutrons present inside the nucleus, which is the nuclear energy. Here the electrons which is present out of the nucleus is going to move out of this atom and it is going to be available in the free space around the material, which makes this electron to be movable. The movement of or the flow of electrons will be responsible for the electrical energy. When we are talking about chemical energy, we always used to think about something which is happening in the laboratory like this. But chemical energy is not only the energy associated with the chemicals. Whatever the regular activities we do, in them also we have the chemical energy. For example, what is the fossil fuels we are going to use? All of them are the components of the hydrocarbons. So they do have the chemical energy possessed inside them. The hydrocarbons, hydrogen and carbon, all of them are bonded with each other. That bonding which is responsible for the chemical energy. Same way, when we are talking about the food what we are intaking, they are also kind of hydrocarbon, or we are having the fat associated with the food, and we have so many minerals and proteins. All of them are going to be made up of with the organic components, hydrogen, carbon, other proteins, vitamin B, vitamin C, whatever we are talking, everything works or they formed because of the bonding between the different chemical elements. So that the food what we are intaking or the food is also having the chemical energy stored inside it because of a chemical reaction. For example, when we are intaking the food will be getting into our stomach, and inside the stomach we have the enzymes which is going to break this food into its particle. So the breaking of food into its particle, and that particles are further going to be disintegrate into this pure elements which will be giving energy to our human cell, body cell, right? So because of the chemical reaction of this either fat or the carbohydrate with the enzymes or the acid present inside the body is going to release out energy. That energy is called as the chemical energy. So as the result of the chemical reaction, what is the energy is going to be released is called as the chemical energy. When we are coming for the last part of it, the mass energy equivalence. According to Newton, mass energy equivalence. So whatever the energy we are going to have, that will be equivalent to the amount of mass which is going to be utilized. That is what is this mass energy equivalence tells us. That is E is equal to mc square, where E is the energy which will be measured in joules and m is the mass which will be measured in kilogram, and c is the speed of the light which will be measured in meter per second, and the value of that is 3 into 10 power 8. To understand it better, let us take this example over here. We always wanted to do workout to reduce our mass, right? Whenever we are doing a workout, the workout is going to consume energy from your body. If it is going to consume energy from your body, that energy is going to be taken from all the unwanted fat what we are going to have. So basically whenever we are doing a work, that is going to be converted into energy, or that is going to be absorbed by the energy. If you are doing a work, that means that you spend some energy for it. So you are doing a work, and for that you need energy. That energy is being taken from the fat. Those fats are nothing but the extra weight what we have, or the extra mass what we have with our body. So this extra fat, which is the mass of our body, is reduced whenever we are going to do work, that is we are spending energy, right? So whenever there is a mass disappearance is happening, that is obviously converted into the energy. For example, let us explain it in terms of the nuclear reaction which is happening inside the sun. So we have two hydrogen which is going to join together. More elaborately, one deuterium and one tritium is going to join with each other. That is, two hydrogen isotopes are going to fuse with each other, which is going to produce the helium. So we are taking the mass of this two of them and the addition of this reactant, that is the mass of the total reactant what we are going to have here is 5.029. As a result of it, we have the product with products which are all being formed. They are going to have the mass of 5.01. See, we have taken 5.029 something. Then the answer what we are getting should be of the same amount. But we are not getting it over here. The reason for that is during this nuclear fusion process, there will be a very huge amount of energy is going to be released. As well as to combine these two to form a new product also we need energy. That energy is being taken from this mass disappearance. So what is the 0.01 unified mass is disappeared over here? That is only used to form the new product over here.